I'm a planetary scientist. Hang on, I've got it, live stream. My main focus is on surface geology, trying to look at planetary data, particularly images, and understand how surfaces formed and evolved over their history. And I've been lucky enough to do that in a lot of different places. Okay, so my story begins really with the Galileo mission. Galileo was a very exciting project. It was a large project to the Jupiter system, and it was a follow-on from the Voyager missions of the basically the 80s. Voyager flew through the Jupiter system and took images as it went through and other data. But we knew there was something very special about the system, and Galileo was designed to go back and study both the planet, its rings, and the satellites in more detail. But Galileo didn't go to plan, and it was my first experience on a space mission. I was in graduate school at the time, and this was where I sort of learned that space exploration is hard. It doesn't always go the way you want. Sorry, I'm having trouble forwarding my slides. Okay, there we go. So this is an image on the left of what the Galileo spacecraft should have looked like. You can see this big sort of inverted umbrella type thing is the antenna. The antenna did not open as planned, but I'll get to that in a moment. Galileo itself was deployed in 1989 from the Space Shuttle Atlantis, and it had a long history even prior to that time, history of delays, partly due to the Challenger disaster and other issues. So by the time it launched, it already was using sort of fairly outdated technology, and it had been sitting in a warehouse, I think, for several years. But it launched in 89, it got to the Jupiter system in 95, and it dropped a probe into the Jupiter atmosphere, and that probe sent back incredible data of Jupiter's red spot. But I mentioned the antenna. The antenna did not open the way it was supposed to, and that this is just an artist's impression of what that might have looked like. So basically just like a broken umbrella. And that resulted in a major reduction of the amount of data that was able to be sent back to the Earth. And I've heard an estimate that we perhaps only got about 10% of the data that was originally planned from Galileo. There was also an issue with the Galileo tape recorder. This was back in the day where data was put onto tape. The tape recorder also had some issues, including getting stuck, and parts of it were unusable. And so that also contributed to the sort of reduced data return from Galileo. Nevertheless, we did get some amazing observations from many different instruments of the Galileo. We call them the Galilean satellites, like the satellites that Galileo himself discovered back in 1610 when he first looked at this system through his very sort of early telescope. And you can see here, these are mosaics or images put together from Galileo data of the 4 major satellites in the system. There are, I think, about 70 smaller satellites, but these are the big 4. And they're very different on the surfaces. And the reason they're so different is related to how close they are to Jupiter and how they interact with each other. They undergo sort of tidal heating, similar to the way we have tides in the ocean because of the pull of the moon. These satellites pull on each other, and Jupiter pulls on them all, but the closest one's the most. And so Io is the youngest. It's the most volcanically active body in the solar system. Europa is pretty young on the surface. We think about 60 million years. So, to us as mere humans, that seems very old indeed, but in geological terms, that's quite young. And we think it may be active today. Ganymede is about half and half. It's got a lot of very old terrain, old heavily cratered dark terrain, and some brighter icy material. And then Callisto, which doesn't undergo much heating at this stage in its evolution, has a surface that's probably very close to its original surface, about 4.5 billion years old, and just covered in impact craters. And so Galileo, to take these data, Galileo went into orbit around Jupiter, and we're looking down here on the top right onto an orbital diagram. You'll see a lot of these in my talk. But Galileo went into orbit around Jupiter and did these kind of petals and flew by the satellites at different times as it was coming around Jupiter. And that's how we got these data sets. So I was in graduate school at this time. These are some of my grad school buddies. You can see them all in their Galileo shirts. And this was one of the rooms that we worked in. You can see this is pretty much what it was like. It's kind of messy. images would come down from the spacecraft, we would print them out, we would be absolutely amazed. The data was at much higher resolution than we'd ever seen, and there were just discoveries every day. It was a really exciting time to be involved. I started out looking at Ganymede. I mentioned that it has these two kind of geology types, the dark terrain, the old terrain shown on the top, and then this younger, brighter terrain. That is either, we're not really sure how it forms. It's either the result of sort of icy volcanism on the surface, or fracturing, or maybe a combination of both, and we still don't really know. And then impact craters, so these kind of holes, these scars on the surface that are formed when meteorites or comets hit the surface, and they're very unusual. When they go into ice, they look very different from the kinds of impact craters we see on the Earth or on the Moon, for example. But I was very interested in dark terrain, and I spent at least the first year of my time on Galileo looking at one of these areas. This was an area we took on the first close flyby of Ganymede, and it's not a very beautiful part of the terrain. You can see from the scale by that crater, you can see most of the crater at the bottom is about 20 kilometers, maybe 13 or 14 miles wide. And I got involved because no one else was that interested in this kind of terrain. And I spent a lot of time mapping it and trying to understand the history, you know, when had the impact craters occurred, where were the highs and lows on the surface, and just trying to understand how it formed. And we actually concluded that the dark terrain on Ganymede is really just a sort of dark lag, almost a lag of dirt on top of an otherwise fairly icy shell. Ganymede, like Europa and Io, is mostly a rocky body, but it does have a considerable amount of ice in Ganymede's case, and smaller amounts of ice in Europa's, and none on Io. So again, it ties back to the tidal heating. Nope, still not going. Okay. My next stop after studying Ganymede for a while was to start looking at Europa. And Europa, it soon turned out, became an extraordinarily fascinating body. And so Galileo had a prime mission, and then it was extended a couple more times because the science was so amazing that it was doing. It wasn't expected to last as long as it did. The Jupiter system has really a vicious radiation environment. It's like a giant particle accelerator. And so these moons are bombarded with radiation all the time, and so is any spacecraft in the vicinity. And so we expected that after a while, all the instruments and all the systems on the spacecraft start to fail just from radiation damage. But Galileo went on longer than expected, and part of its continuation was to focus on Europa. One of the most exciting results from Galileo was from the Galileo magnetometer, and by I think 3 flybys of Europa, where we were quite close, we discovered that there was an electromagnetic signal coming back at the spacecraft, which we realized was the result of a saltwater ocean beneath the surface. So this is a rocky body. It's about the size of the moon, and it has, we think, a global ocean about 100 kilometers thick, maybe 70 miles thick, and then it's got a crust of ice that's maybe 20 kilometers thick on top. So this was a huge discovery, and this kicked off a whole future field in ocean worlds, right? So, and I'll come back later to why that was important. Europa's surface, we'd had hints from the Voyager data that this was also very unusual and very exciting. And as you can see here, these are some of the terrain types on Europa. Really unusual, certainly an alien world in every sense. These ridged plains cover the whole surface, and we know they are related to tidal heating, where Europa is squeezed every orbit between Io and Ganymede, but we don't really understand why these ridges form and why they're so widespread on the surface. Another major terrain type is this chaos terrain, which it looks like the surface ice has been just broken up into plates. And we think this forms from material moving slowly up through the ice crust by convection. If you can see, I have a lava lamp behind me. It's the same kind of process there, where we think that material comes up maybe from the ocean or maybe just in the ice, like convection, comes up through the ice, bursts through the surface and forms this kind of terrain. So these are the two main types on Europa, and it was just fascinating. And despite Galileo, we still don't really know how these form. And this is just a sort of regional view of the surface, showing how many of these kind of fractures or fracture-related features are on the surface. And again, no impact, very few impact craters. So we know the surface is very young because we count the number of impact craters. The longer something has been sitting in space accumulating craters, the older it is. This is not very old. So I was very excited this time, not just to be able to do science on this data, these data sets that were coming down from a spacecraft that was in orbit around Jupiter, but I was also invited to help out with some of the mission planning. In this case, planning of the image sequences. So this was done at the Jet Propulsion Laboratory. They were running the mission. And these are horrible pictures because I took photos of paper copies from an old file folder that I still have. But I thought this might be interesting to you. So on the left, this shows you how we planned where the images were going to fall on the surface. If the antenna had opened, we would have been putting images over everything, but it didn't. So we had to be very careful about where we put things on the surface. And so here on the left, you can see there are actually 6 different frames here. We always overlap them a bit because we don't always know our pointing is very good. And at the bottom, you can see this says G1 Europa. So G1 actually meant that the main petal of Galileo was flying closer to Ganymede than anything else at this time. But it also looked at Europa while it was doing this. So Europa was further away. And these images were going to be taken starting 21 minutes after closest approach of Europa, and then up to an hour afterwards. And you can also see, if you look at the top right of the left image, 1.6 kilometers per pixel. So these were what we call regional to global images. And then on the right, you can see a sequence where we plan to sort of start putting tiles down on the surface at high resolution here, about 234 meters per pixel. So if your campus was there, you'd probably resolve those. And we would make up an image mosaic. This was taken on the 15th flyby. This time Europa was the closest target, about an hour after closest approach. And this just shows you another version on E17. And you can see on the right hand side what that actually looks like. Once you get these images back, you put them together into a mosaic, and then you overlay them on a lower resolution image. So this was just an incredibly exciting time to be involved in this mission. And it was from doing these sort of mission planning things that I decided that I wanted to go into missions as a career. So much as I loved science, and I knew I would always want to do science, and I always have done science, I knew that I also wanted to be at a mission provider. And so my next job, I got a postdoc position at the Applied Physics Lab in Maryland. And this is where we get not quite as cold, but here I worked on the near-Earth asteroid Rendezvous. And I say here, taking advantage of failure to further my career. It wasn't really a failure, but it was a mission event that didn't go quite right. And I happened to be in the right place at the right time to take advantage of it. So NEAR was a small spacecraft that was sent to explore an asteroid, the asteroid 433 Eros. It's the 3rd largest asteroid that we know of, and it's about 30 kilometers long. You can see on the left that between the Earth and between Mars and Jupiter, we have the main asteroid belt, right? So this is an area of sort of rubble and debris, a region of bodies that never quite made it into planet status. They didn't quite come together enough. And on the right, I'm sorry, this is quite a bad image because this stuff all happened 20 years ago. So it's the best I could find. But some of these asteroids, for various reasons, get kicked out of the asteroid belt into other orbits. And Eros is one such asteroid that got kicked into what we call a near Earth orbit. It actually crosses the orbit of Mars. It doesn't cross the orbit of Earth, but it comes closer to Earth, not nearly close enough that we have to worry about it for hundreds of thousands of years, I think. But we were trying to understand, how do meteorites, space rocks that we find on the Earth, and you can see one top right here, how do they relate to the asteroids in particular? And can we establish what are the parent bodies of some of these space rocks? And so Eros was thought to be a parent body of one of the most common types of meteorite, chondrite meteorites. And it also, the fact that it came close to Earth made it relatively easy to go and visit. So that's what we did. It's gone again. So this is just an artist's impression of the spacecraft. It has four these wings are solar panels. And on the right is just a diagram showing the instruments. I'm not going to go into them all, but I was involved in the multispectral imager. So I've been involved in images throughout my career. I just want to point out here, you can see the instruments are all around the bottom of the spacecraft, around this ring-shaped thing. This is called an adapter ring, and this is where we attach the spacecraft inside the launch vehicle. So here on the left is another image of NEAR. The solar panels are folded down, right, so that it will fit in this rocket. We wouldn't be able to launch them if they were out, so they deploy after launch. And you can see it on the right. This is inside its launch vehicle. You can just about make a person out in the bottom if you look carefully on the left-hand side, so you can get an idea of the scale. And the rocket is basically like a shell, like a clam shell. And we load the spacecraft into the nose cone of the rocket, then seal it up, and then off it goes. So NEAR launched in 1996. It was the first in a line of missions called the Discovery mission or Discovery program. These are $500 million. It was a lot less at that time, but now they're about $500 million program missions that NASA flies. They're considered low-cost missions, which always cracks me up because I can't imagine much else where 500 million would be considered low cost, but they're relatively small planetary missions, very focused. And this is another one of those views where we're looking down on the sun. And I'm sorry, again, the resolution isn't that great, but I wanted to point out a couple of things here. We launched from Earth in 1996, I just noted. We were supposed to go into orbit around Eros, I think in 1998, in December 1998. But the event, the orbit insertion event, if you like, that was supposed to get us captured into orbit around Eros, or at least into a place where we could start orbiting Eros, didn't quite go as planned. And that's where I got the benefit of that, because we had to go round for another year and pick up Eros again a year later. And then we did get successfully into orbit around Eros. And I had just finished my PhD in November 99. And so if NEAR had gone into orbit at the right time, I was still in grad school. I wasn't available at that time to come and work on it, and the job wasn't available. And so because of the delay, I was able to apply for the job at the right time. Luckily, I got it, and I was able to come to the Applied Physics Lab in Maryland and work on this Eros mission. And I also want to note on the bottom left, the Eros arrival is February 14th, 2000, Valentine's Day, because we're going to Eros. And I know you've heard from Alice Bowman in the past. I'm not sure if this has come up there, but our mission designer at the time, a guy called Bob Farquhar, who was just a genius, he used to plan these major mission events around events in his life, particularly his wife's life, like his wife's birthday or their wedding anniversary. He was a very romantic soul. And so we went into orbit on Valentine's Day. This is a sequence of some of the first images as we were approaching Eros. It's a very odd shape. It's like a potato or an old boot. And it spins about once every 5.5 hours. And it's sort of, if you imagine picking up a boot and throwing it sort of forwards, that's how Eros rotates. So we were orbiting it while it was going around in its orbit and while it was rotating, and we were imaging the surface. So it was a kind of a fun sort of activity. And we started out in a higher orbit and slowly rotated in until we were as close as we could safely be without some of the pointy ends coming back to hit us. So you know, it was quite a geometrical challenge. This is just a close-up view of the asteroid. I mean, we'd never seen anything like this before at anything like these resolutions, and we just got closer and closer as time went on. This is jerky on my screen. I know it's jerky on your screen too, but this is a sequence of images that we put together. You can see along the bottom, taken in December 2000 at, I guess, about half an hour apart, I think. So you can get at least a feel for what it might be like to be on the spacecraft going around this slowly spinning body. We also had to wait. The reason we were in orbit for a year, the prime mission, was also because we could only see one half of the asteroid was lit. in the first 6 months, and we had to wait for the seasons to change so that we could see the other half of the asteroid. But a tremendously amazing mission. I was particularly interested in structure, as in fractures and cracks on the surface. We care about those because, first of all, we don't know much about how asteroids form and evolve, how the pieces kind of glom together, or are they big shards of larger bodies? And you can see some examples here. But also for planetary defense. We just launched a spacecraft called DART from APL, which is going to see how easy it is to deflect a very small asteroid, or actually it's a moon of an asteroid. But this shows you that it would be a lot easier to deflect something that's a pile of rubble than something that's a big chunk of rock. And so what I was doing was mapping out grooves and fractures on the surface. And what we realized was that, if you've got grooves going over large portions of the surface, it's probably a solid piece of rock, because you can't make cracks in piles of rubble, right? You can try this with crackers later. And so we think Eros is a pretty coherent shard of something. So we ended the mission. We were in a 35-kilometer orbit, and we knew we were eventually going to crash on Eros, but we thought, let's do a controlled landing. No one had ever orbited an asteroid at that time, and no one had landed on one. So again, this was the brilliant Bob Farquhar sort of planned all this out. And you can see we're looking down on Eros. The south pole is actually not where you might think. You might think it would be on the pointy ends, but it's actually on the spin pole in the middle. And so we went down there. This just shows you the final landing site in the bottom left, where we think we landed. Of course, we didn't have anything in orbit to see where that actually was. And an artist's impression on the top left. And then on the right-hand side, you can see the last 4 images as we were slowly coming down towards the surface. And the camera was amazing. We didn't expect to be able to resolve the surface. From this close, we thought it would be blurry, but it was actually amazing. And then in D here, you can see where you've got these dropouts in the image. That was where we stopped getting data back from the camera. And I mentioned earlier that the instruments were all around this sort of adapter ring on the bottom of the spacecraft. So we came down onto that ring. And so once we were on the surface, we couldn't take any more imaging data, but we were able to still take data from a couple of our other instruments. The magnetometer was one, although Eros turns out it's not magnetic at all, so that was unfortunate. But also our gamma ray and neutron spectrometer, so we learned a little bit more about the composition from that. So really very exciting mission. And as a postdoc, I was sort of the lowest, most unimportant person on the whole mission, but they still let me do science, and I got to see these images coming down from the spacecraft every day. So really exciting. Just checking time. I think I'm doing all right. So next we get very hot. Messenger at Mercury. Messenger, I don't actually remember what Messenger stands for, but it's a long name. It's actually a backronym. It's not a proper acronym. But this was a surface and remote sensing mission. We were looking at the environment of Mercury. We were looking at the surface of Mercury. We were understanding the composition, looking at the poles. Really incredible mission. Now, Mercury is very hard to see from the Earth. It's hard to study with ground-based telescopes. I'm sure some of you in the audience, if you're astronomers, you will know that. It's very close to the sun, so it's hard to see it. And the times when it's best to see it are also at dawn and dusk, when you're looking through the Earth's atmosphere. So it's never been that easy to study. We did go there once with one spacecraft, Mariner 10, in the mid-70s. And Mariner 10 flew through the solar system. It launched from Earth, it went past Venus, and then it flew by Mercury while it was going around the sun. It went by Mercury 3 times, but it didn't get very close to Mercury. So we had some data, but we only had data from one hemisphere of Mercury, and a lot of unsolved questions. This is always the case with missions. You get data, you learn a whole lot of amazing things, but then there are always more questions. But there was a lot we didn't know about Mercury. In particular, we didn't know about its history. We thought it was had been inactive for a very long time. We didn't know if it had volcanism on the surface. There was so much we didn't know because we hadn't got that close to it. So the reason no one had been into orbit before was that insertion into orbit requires a lot of energy, right? Something we call delta V, a big change in spacecraft velocity. And for a long time, no one had even figured out how we could get into the right position to do that. This was actually done I think in the late 1980s, by someone at JPL, a woman at JPL, who was a mission planner, figured out how you could make this happen. The other challenge, of course, is that you're very close to the sun. Both Sun and Mercury's day side, which can get over 800 degrees Fahrenheit, pose really difficult challenges. So it's not a really great environment, and it's not somewhere that you would easily go to. So these pose some problems. So how did we address these problems and go into orbit despite all this? Well, the spacecraft itself, you can't really see it so much on this view, but it had 3 very large tanks of propellant, of fuel. It was almost like a flying fuel tank. And so these were needed to get into orbit around Mercury, to do this burn to get into orbit. The structure itself was very low mass carbon fiber composite, so like a pool cue, I guess. We needed solar panels because we were not going straight to Mercury. We were first going outside into the solar system. We were going past Venus, and it was going to be cold, so we needed a lot of solar energy there to keep us alive, but we didn't need so much when we got closer to the sun. And so these were mirrors, and they were also basically on stalks, so we could turn them edge on if we didn't want as much power. What else do I want to say here? Oh, and we put everything behind a sunshade. So we could have done this 2 ways. We could have just developed a lot of technology and a lot of instruments that could survive 800 degrees, but we did something much easier than that. We just stuck everything behind a sunshade. So in front of that, the temperature was many hundreds of degrees. Behind it, everything was at room temperature, which is just amazing. So it was much easier to operate the spacecraft. And how do we do that? We put this sunshade on, and we covered it in ceramic cloth, which is the same kind of cloth that they were using on the space shuttle to stop it burning up when it came through the atmosphere. Here's a picture of the spacecraft. It looks a bit like the near spacecraft I showed you. This is getting a vibration test. Again, the solar panels, you can see the mirrors on there, and again, they're folded. A lot of people in the room. And this just shows you, again, these are all acronyms for different instruments. It was a very capable payload to do particles and field science and all this remote sensing science. I worked on the Mercury dual imaging system, which is this thing in the middle, which was 2 cameras, a narrow angle camera, which was like a telescope. We were able to see the surface from far away, and a wide angle camera, which allowed us to see large areas of the surface at once. And it had different color filters on it. And these cameras were mounted on a gimbal, so we could turn and look at the surface from different parts of our orbit, and that became important later. We launched in August 2004. It's always a big party at the launch. You're either in the sort of official launch area, or I think in this case, we were on the beach, which is where a lot of the engineers go. It's just one big party, so if you've never been down to Florida to do that, highly recommend it. Sometimes it goes with it, sometimes it doesn't. This is a very complicated figure, and I apologize, but it shows you how many times we had to go around the sun to slowly kind of creep up on Mercury, right, and get ourselves into exactly the right place that we could fire our thrusters and go into orbit. And this was a very complicated orbital dance, as you can see. If you look along the bottom, you can see we launched in 2004. We actually got into orbit insertion in 2011, so 6.5 years of cruise times, we call it. But during that time, we flew by Earth, we did 2 flybys of Venus, and we did 3 flybys of Mercury. And each time we used a little bit of their gravity to help tweak our orbit and get us where we wanted to be. So orbit insertion, this was the orbit, the initial orbit. Eventually we sort of narrowed it down, and it got down. This was a 12-hour orbit. We got down to an 8-hour orbit, and we're looking side on to Mercury. So north is up. So you'll see it's a very elliptical orbit, and that was for 2 reasons. One was that we could live a lot longer. We didn't need as much propellant to get into this orbit as if we got into a purely orbital, a circular orbit. But we could get into an elliptical orbit. We could live a lot longer. And actually, there's a European spacecraft, Bepi Colombo, that is en route to Mercury now, and it's going to go into a circular orbit. So it'll be a lot closer to the whole surface, but it's only going to last about a year. We lasted, I think, 3.5 years. But the other reason for this kind of orbit is that it's 11 times hotter at Mercury than it is here on Earth. So we knew we had this aggressive thermal environment, but we were also getting radiated heat from the surface every time we flew over it. And so by doing this big elliptical orbit, we could get hot and then cool down again, then come back and get hot again. It didn't it didn't hurt us too much. So you don't go into orbit around a planet every day. This was a huge event. We had a big event here at the Applied Physics Lab, a huge auditorium. I don't have many photos, but someone had sent me this photo. This is me being interviewed. We were sort of had a lot of hours of material while we were waiting for the actual burn for the orbit insertion event. And when that happened, it's quite a breathtaking moment, because you've got this lag between us and Mercury, and I don't remember exactly how much it was then. I think it was like 8 to 10 minutes or something like that. So things happen and you don't know they've happened until later. And in this case, we were doing this burn that I believe lasted about 15 minutes. And it was very important that we got it spot on. And so what we're looking at here is, again, I apologize for the quality of these. This was a photograph of the screen in our big auditorium with hundreds of people in there. And we were just watching a radio, basically a Doppler signal from the spacecraft. That's all we had to tell us where we were in time and tell us what was going on. So you can see the Doppler shift on the left and time. So we could tell that the spacecraft was moving, but we couldn't tell anything else about it. We couldn't, for example, tell if it was spinning or anything like that. We could just tell where was it moving in the way we wanted it to go. And this was really important, that the burn started and stopped at exactly the right time. If we had burned for too long, we would have got into an orbit that was too close, and we would not have lasted very long. We wouldn't have fulfilled our science goals. If we hadn't burned for enough time, we would have not gone into the right orbit at all, maybe not even orbit, and we might have been in something more chaotic and still going around the sun. So this was really critical. Happy to say it worked perfectly. This is, again, from the screen in the auditorium, a photograph of our principal investigator, Sean Solomon, in the middle here, just after this had happened. So you can see by the enormous smile on his face, he was pretty happy. And it taken at this point about 10 years, winning the proposal to get the money to do this, getting there, building the spacecraft. So 4 or 5 years there, and then 6.5 years, and finally we were in orbit. And this was one of the first images. Actually, we got this from one of the first flybys of the hemisphere that Mariner 10 had not seen. I think I'm going over time here. I'm going to speed up a little. We also did something called false color images. We could use different color filters to tell different compositional variations on the surface. And this is just a sort of high resolution views of some of the incredible geology, very unusual impact craters in the top. We saw evidence of pyroclastic material, so airborne material that had come out of these volcanic vents. This is the top right. Large volcanic areas of volcanic plains. We definitely proved that volcanism had been alive and well on Mercury, not only early in its history, but it actually extended a lot longer than we thought. And then these incredible sets of cracks. This is inside one of the giant basins, Caloris, just a whole wealth of amazing things to discover and explore. So I won't go through all this, but Messenger was a tremendously successful mission. 8 billion miles traveled, 29 trips around the sun, and the bit that I'm most excited about, over 250,000 images of Mercury and of other bodies returned to Earth. So just a truly amazing mission. Meanwhile, while all this was going on, I was still working to get back to Europa with a small group of us. We realized how exciting and important Europa was. And why is that? I mentioned that it had this ocean, and here's a sort of cutaway view. And we think that the ocean's about as conductive as seawater, right? So why do we care so much about water? First of all, Europa has a lot of it. If you actually compare it to Earth, it has more water than Earth, which sounds crazy given their relative sizes. Earth's oceans cover 2/3 of the surface, but they're very thin on a global scale. They're like a couple of kilometers on average, whereas Europa's ocean is 100 kilometers thick, and it covers what's inside the whole of Europa. And so actually, when you do the numbers, there's more water on Europa than on Earth. But even more important than that is, why do we care about about water? Water, we think, is one of the critical ingredients for life. The other two are chemistry. Do you have the right ingredients for life to evolve? and energy. So we know we have the tidal heating. We know, or we're pretty certain we have water. We're not so sure about the chemistry. We got some very preliminary composition results from Galileo, but we don't know much about it. So we realized it was really important that we go back to Europa, because we think it might be a habitable world, right? Whether there's life or not there is another question, but are the ingredients for life there? And so a number of us worked from 1999 to 2013 to try and get a Galileo follow-on underway, because Europa was such a special place, perhaps has the highest astrobiological potential anywhere in the solar system. And apologies again, these are some of the many studies we did. I actually didn't get involved till 2004, but we wrote study after study. NASA would give us a little bit of money. We'd get a small group together. We'd look at concepts, all kinds of different concepts. And we'd go back to NASA and they'd say, that's great, but we don't have money to fly you right now. You'll have to wait. And usually they were funding a Mars mission, which got a bit frustrating. So this went on in the background while all the other things were happening. And this is just to give you an idea of what life is like when you're doing studies. This is what we call a war room, because you're going to war, you're trying to win this mission. And you can see here just a science section up on the wall. We spent hours, many hours, months, probably years in these rooms in the dark, trying to write more science and come up with more exciting ideas. We would break into small groups. This is, I think, me talking about Ganymede geology. One of these concepts went to the whole Jupiter system. Here's one late night here at APL, the Applied Physics Lab, where we didn't even have enough wall space, so we ended up putting that proposal on the floor. And radiation was one of the reasons why we didn't get selected for a long time. People didn't believe we could go into orbit around Europa and survive long enough to do the science that we wanted to do. So we spent a lot of time showing that that was not the case. And we had a lot of prototypes. These are made out of paper. This is in the days before 3D printing, with straws for antennas. The spacecraft would evolve in various different ways. But finally, in 2013, after many iterations, we got our mission. It's called Europa Clipper, named after the clipper ships of old that used to ply the seas, on these trade routes. And this was a really incredible moment. If you are interested in learning more about what it takes to get a mission off the ground, and this is quite in depth, I would recommend this book. Those of us that worked on the mission through all these proposals and studies are in it. We're not getting any money from it, but if you're interested, this could be a fun read. But it is very in depth about the sort of how NASA really works. So the Clipper science objective is mainly to explore Europa, to investigate its habitability. Is it a habitable world? Not is it inhabited, but is it habitable? We want to study the ice shell and ocean, understand where the water moves around. If there's, does water get from the ocean up to the surface? And if so, how does that happen? We want to understand the composition. Does it have the ingredients for life? And we want to look at the geology, because it's really cool, right? It's the coolest geology in the solar system. And we also think it may be active today. There have been some hints that there might be plumes coming off Europa. We don't know for sure, but we're going to go and find out. So we will launch, and I'm sorry this is very dark, but we will launch in 2024. That's the current plan, in October. And we will be going on a commercial launch vehicle. We expect to get into the Jupiter system in 2030. So already nearly 20 years after Galileo, 5.5-year cruise. So, in this job, you need to have a lot of patience, I think, to do the outer solar system. This just shows you what our orbit is going to, start over. We're not actually going to orbit around Europa. At the end of the day, it proved to be too difficult and too expensive, and we weren't sure we could last long enough to meet our science goals. So we're going to orbit Jupiter, and we're going to do multiple flybys of Europa, about 49 at last count. And you can see this should be rotating. The altitude changes as Jupiter coming by in the background, just to give you an idea of what it will be like. But we will be at different altitudes as we fly by. And it's going to take us about 3 years to collect data across the whole surface. You can see there's one area that it's actually quite hard to get data. So we'll be viewing that from further away. This is just an image of the first science team meeting we held at the Jet Propulsion Laboratory. And this was the moment for me where, after all these years, it finally became real. And we're all here to prove it. So that's very exciting, 2015. I did want to show this image. There weren't many women on Galileo, right? I was in grad school then. I was one of the few women in grad school. And we're very excited that we have, I think the team is about 20% women on Europa Clipper. It's still not quite where we want it to be, but it's a lot further forward than it was on Galileo. And so this was just a selfie someone took at one of our evening events. And I'd like to point out that the lady in the middle here is Margaret Kibbleson. She's a professor at UCLA, a physics professor, and she's 93 years old. She's leading our magnetometer instrument. She's absolutely amazing, absolutely sharp, really active. She's just an incredible role model, and she's been an amazing role model, I think, for all of us here. We're building spacecraft right now. We're delivering instruments. This is the propulsion module. We built that at the Applied Physics Lab. Here it is at the Goddard Space Flight Center being tested. And you can get an idea of the size of the spacecraft from this. So this isn't the rocket, right? This is going on top of the rocket or in the rocket. And then once we've got out of the Earth's gravity, this will get us into the right orbit when we're at Jupiter. So it's pretty massive. So I think I'm going to wrap it up there because I know I'm coming to the end of my time, but we're very excited about the opportunity to go back to Europa. This is just an incredible world. And up here on the left is my colleague and friend, Bob Pappalardo. He's the project scientist of the Europa Clipper mission. So he's responsible for all the science there. But he always likes to show these 4 little stars, which are the drawings that Galileo did in his notebook the first time he saw the Galilean satellites. And just to show how far we've come in the 400 years since Galileo first turned to look at this system. So with that, I will stop and take any questions. Thank you very much.
Thank you very, very, very much.
I know that was a lot. That was a lot to take in.
No, it was wonderful. I feel like I've had this full tour of the solar system and I'm very happy. Maybe if we stop sharing the screen, we could see if people are raising hands. I'm already seeing a couple comments in the chat that I can ask. Here we go. The first comment was not necessarily intended for you, but it's a suggestion that Margaret, who you had mentioned, the physics professor at UCLA, be a future speaker at Roger that. What is her last name?
Kibbleson, Kivelson. We call her Margie Kibbleson, but she's kind of a legend. And when she was, an early career, she's got photos of herself, standing with all these guys. She's like the only woman in all of these photos. She really blazed a trail, and she's just a brilliant scientist, wonderful. She's one of the people who discovered the ocean on Europa from the magnetometer data. Wow. She led that group. So yes, definitely invite her. She'd be great.
That is amazing. Couple questions I see so far. Samita Rhodes, who's one of our co-organizers, she says, so Europa is a great source of interest because of that large body of water. But are there other objects of interest, other moons or planetary bodies that are poised to be the next big thing?
Yes, there are. Enceladus is a huge one. Enceladus is much smaller than Europa. Europa is about 3,000 kilometers in diameter. So, if you looked across it, Enceladus is only about 300 kilometers. So I think of it as it would be the size of England and Wales, which makes me a bit sad. But Enceladus has plumes of, we think, ocean water coming off it. We've actually been able to sort of test the composition of those plumes using the Cassini spacecraft, which I didn't unfortunately get to work on. That would have been great. So Enceladus is definitely an ocean world. What we're not sure about Enceladus is, has that ocean been there through its 4.5 billion year history or not? Like, we don't really know why such a small body isn't frozen out yet. And so that's one of these mysteries. But these two worlds, I would say, have started a huge interest in ocean worlds. And one of the things I didn't show you was that I have been trying to get a mission off the ground to go to Triton, which we also think is an ocean world. And that's Neptune's moon, so 30 AU. So what, 5 times further than Jupiter, 6 times further than Jupiter. Can't do simple math. But yes, we think actually there might be a lot of ocean worlds. A lot of these icy satellites might be ocean worlds, and maybe ocean worlds are actually quite common. We don't know yet. But the other thing about Europa's ocean is, of course, it was only, what, 30 or so years ago that we discovered hydrothermal vents on mid-ocean ridges. And the fact that there was life in places in the Earth where there's no light. Prior to that, we thought you needed photosynthesis. And now we know you don't. So suddenly the whole solar system becomes very, very interesting, right? And so that's another reason why Europa's ocean, you know, we don't know, we think it's salty, but we don't know how salty it is. It might be too salty for life as we know it. But yeah, so I think this is kind of the revolution in planetary science right now is ocean worlds for sure. So thank you, great question.
Definitely. And I think it's so exciting to see the interdisciplinarity of engineering, biology, geology, everything working together. Yeah. And it's fantastic. Yeah. Dwayne Day had a comment, which was, what are the specific,
Dwayne and I are buddies, so.
What are the specific science goals for the Clipper mission?
Oh, the Clipper mission. I thought I had that on the slide, actually. We want to understand the structure of the ice shell. We have a radar instrument, which is the first time we'll have gone into the third dimension on any of these icy bodies. We may not make it down to the ocean, but we hope to at least understand how material is moving through the shell. We are measuring the composition of the surface with several different instruments. So to understand, like I talked about the ingredients for life, what do we actually have the right ingredients? I think one that we're always looking for is phosphorus, and no one's actually found that on an outer solar system satellite yet. So, you know, nailing down what we understand about the ingredients is important. We're also measuring the environment. The magnetic field is huge. The Jupiter system and the radiation environment will be measuring all of those things. We'll be looking for plumes. If plumes are there, we're flying low enough that we could conceivably fly through them. They'll be very nebulous. They shouldn't hurt the spacecraft, although we'll be careful about that, obviously. But we'll also be doing that as well. And then we'll also be taking very high resolution imaging of the surface. We'll do global maps for structural geology, understanding the tidal stresses and other stresses, so we can understand the evolution. But we'll also be taking very high resolution images of the surface, because right now, the next step in Europa's evolution, mission evolution, let's say, is a lander. But at the moment, we don't have high enough resolution images to land on the surface safely. And if you remember all those ridges I showed you, that one image of all those ridges cross-cutting, you would not want to land on that unless you could find a smooth, flat place. And we haven't found anything that's smooth and flat on Europa. So we want to find safe spots for future landers. So it's a very high level for Dwayne.
We have a couple more questions, then we're definitely going to have to wrap it up because we've got another
person. Sorry, I did go long.
But the two questions, I'll read you both and I'll see if there's a way that you can connect them. I don't know if you will be able to. One is from Alice, wanting to know if you have any thoughts about Triton being a cousin/twin of Pluto. And then Kid Ma, who's a professor here at GVSU, wants to know if the 250,000 Mercury images are publicly available.
Oh, yes. The
totally
images
unrelated.
Yes, no, the images are all available in the something called the Planetary Data System, the PDS. Everything is available there. It doesn't mean it's necessarily easy to use. If you would like to go somewhere where you can just look at a lot of images and enjoy them, just sort of more public, kind of user-friendly, I would suggest the Planetary Photo Journal. You can kind of cruise through the whole solar system. And right now they've got a lot of Europa Clipper hardware images, but they've got Europa images as well. And Mercury's up there, and Eros is up there. And to answer Alice's evil twin question, we think that Triton used to be in the Kuiper Belt, and it probably was very like Pluto, but at some point it came through near Neptune. We think it was one of two bodies that were probably going around each other and came too close to Neptune. One of them we think got captured into orbit around Neptune, and the other one, just due to conservation of angular momentum, was flung out of the solar system. So Triton is interesting because it may be indeed a twin of Pluto, but a different twin that has been evolved by being melted in the interior and being in the Neptune environment instead of being out in the Kuiper Belt like Pluto. So it's a fascinating body. And the more we've learned about Pluto, the more we can now predict about Triton. Now we've got hypotheses we want to go and test. So I hope we get back there. Hope I get to see it. I'm not too old. Oh, I think I'm muted.
I am muted. Thank you so much. This has been a fantastic talk. I feel like I've had this wonderful journey, and I'm sure our guests feel the same way. Thank you so much for speaking. And thanks to everybody. There's a survey in the chat. We have Sarina Salido coming up at 2 o'clock. And please stay in touch, both the audience and Louise Prockter. So thank you very much.
Thank you very much. It's been fun. Have fun. Enjoy the rest of the day.
Bye.
Bye.